Okay, let's begin. So where should I start? Imagine that you have a data set where you have the blood pressure, and then you measure a patient's blood pressure average for systolic blood pressure average for maybe a week, okay? And then you want to use that to predict whether this person is going to have a heart attack within the next 10 years or something. Okay? It's important research to do, right? People would want to know such a thing. So let's say there was some guy who had systolic blood pressure of 130, and then he did have a heart problem, heart attack. So, red. Okay. But then, you know, some people can have high blood pressure, like 135, and have no problem. Right? And then you gather a lot of people, and then you see that, oh, yeah, indeed, if you have high blood pressure, you have people like this, high blood pressure with heart attack, and if you have low blood pressure, usually you're okay, right? But then maybe occasionally there are people who have other heart conditions that's not just blood pressure related. They might have some genetic problems, you know. Right? So you have such a data set. So I'm graphing it for you to understand the relationship between the blood pressure and the heart attack. But imagine that you have a spreadsheet of everyone's blood pressure and then the incident of heart attack within 10 years for that person. Okay, and so the heart attack column will be either yes or no, right? And then the blood pressure will be numerical numbers. Right? Now what you can do is you can do something called dummy variable. Which is to make no heart attack would be encoded as 0, and yes, heart attack would be encoded as 1. Yeah. So using a dummy variable, you can take a categorical data and convert it into a numerical one so that you're able to process it using functions. That's one thing. Now, what do you do if you have several categories? So, for example, I sent you in the homework car data set. There were like manufacturers, right? There was a Hyundai, Honda, Kia, Ford, Chevy, and stuff like that, right? In those cases, you can use a vector of zeros and ones. So, for example, Hyundai could be 1000, Honda will be 0100, and the other one be 0010, and so on. And those are called one-hot vector. So there are various ways to convert text data into a numerical one so that you can apply numerical analysis to it. Okay? All right, so once you have that, then think about what the picture will now be. It will be like, these will be zeros because there's no heart attack, right? But occasionally you're going to have 1. So here's this will be the blood pressure axis, and then this will be the heart attack axis. It will be like this, and then we'll have 1, and then here. Something like this. Okay. So I've converted this graph into this graph so that now the prediction would be being able to tell whether it's a 0 or 1. Our goal is to find a function that would behave very close to this one. And one possible approach would be to say you want to just do a linear regression, which is not too bad. I mean, think about a line that would have the least error, least mean squared error from this data. It would be something like this, right? Do you agree? That would be kind of mimicking what's happening. Okay? So this will be a simple linear regression. Just linear regression. But we don't like that because, first of all, it doesn't really reflect the fact that the y values are 1s and 0s, right? It's not 1s and 0s. The linear regression will then produce values that are negative or positive, right? And it's a somewhat of a similar situation when we're trying to fit the the parabola using linear regression. It kind of did the job, but it didn't really give us the right answer, right? But then when we added a new column with t squared last time, and we got this quadratic approximation to the data. So quadratic regression actually gave us a much better fit, which gave us the original theoretical curve, right? So it's similar to that. You really don't want to approximate it like this. Rather, what you want to do is to come up with a function that's something like this, okay? Where it's not just simply a matter of getting the correct value. Rather, the meaning of this yellow curve, which is called, what we call the logistic regression. Logistic regression. This logistic regression will have an added meaning that each value represents the probability that you're going to have a heart attack. Okay? So it kind of makes sense, right? So if you're somewhere here, that's a blood pressure like below 110. That's like, oh, that's fine. You're unless you have some really terrible genetic condition or something, you'll be fine. You're going to live healthy, right? And then if the blood pressure measure is something like 135, and then the doctor will get angry with you and say, what are you eating? Are you doing exercise? All the things that I hear when I go to my doctor. Well, anyways, so and then they're gonna give me a warning that you're gonna die of heart attack. That's what they say, right? Okay. So what you want to generate is a curve that will give you probability varying from 0 to 1, and that's called logistic regression. Now, this curve here is called the logistic function. And the simplest form would be 1 over 1 plus e to the negative x. It's also called sigmoid. Logistic function, sigmoid. And you can just draw this curve as if you were taking calculus 1 all over again. So if you plug in 0, what do you get? 1 over 1 plus 1, which is 1/2. So it's 1/2 right here. Okay. Now if x is really large, what is e to the negative 100, for example? What kind of value is this?
Really small.
It's very small.
Zero.
Yeah, it's close to 0. So if this is close to 0, what happens to the overall value? 1 over 1 plus 0 is 1. So you see that as x goes further to the right, it gets closer and closer to 1. Okay. What if x is negative? Well, negative of negative is positive. So for example, if x is negative 100, then this will evaluate to 1 plus e to the positive 100, and this is a humongous value. So if you divide 1 by a very large value, you get a value close to 0, right? So you get something 0. So that explains why as you move to the right, it gets closer and closer to 1, whereas if you move to the left, when x is negative, it gets closer and closer to 0. Okay? And this function is called the logistic function. I looked up Wikipedia some time ago trying to figure out why they call this the logistic function, and I couldn't really make sense out of it. It seemed like there were some, you know, a lot of the old math books were written in French because French had advanced calculus, and as they were translating, some of the words got translated in a weird way. So I really couldn't find the reason why this is called a logistic. Okay? It's just called logistic function. Yeah, not much of a reason. And trying to fit that into this sample is called the logistic regression. Yes?
So 1 and 0 are both asymptotes, right? Where
Yes.
it would never touch the...
Oh, that's a good point. Yes. So what you end up realizing is that if you fit the logistic regression to a data, it will never give you exactly 1. It will only give you values close to 1. Also, it will never give you exactly 0. It will only give you values close to 0. Which is, in a sense, what we like. I mean, we never know for certainty. Right? Yeah. Like, having blood pressure 180 doesn't mean that you're going to be certainly having a heart attack. I don't know. Is that true? Maybe it's true. Yeah. But, you know, some people have really high blood pressure, but then they manage to survive. Yeah. 165?
Yeah.
You have to go to the emergency room right away. All right. Okay. So that's the idea. So if it's just a single predictor or single feature that you're given, predicting what's going to happen doesn't seem like a hard problem to do. In fact, you don't really have to resort to these fancy things. You can just say, oh, it seems like 130 is like a good dividing line. People above this, you should be warned, and people below this, you're fine. You have a question?
No, I was just going to ask like, what you would prefer to cut off, which is just that. So.
Oh yeah. You just cut off, right? And yeah, you can try various things and figure out where the cutoff is, right? The more harder case is when you have many predictors. So, for example, now think about the case when you have blood pressure versus cholesterol level. So then there should be like some people who have had incidents of heart attack here, maybe some here, just outliers. And then most of the people who didn't have heart attack will be somewhere here, right? And maybe some here. Something like that. And then in such a case, if you have these two, then your input will be x1 and x2. Okay, your feature sets will be x1 and x2. And what does it mean to have a logistic regression to this one? It means something like this. You want to have a two-dimensional version of this. It's like a surface where it's 0 here and then it goes up and it gives you 1 here. Makes sense, right? You want a two-dimensional graph. And you might ask, like, how would you, like, what's the best way to distinguish between somebody who would have a heart attack and who wouldn't have a heart attack? Well, the threshold usually is 0.5, right? But you know, like in some cases, if you're a family doctor trying to really be cautious about your patient's health, you might want to reduce that threshold to like 20% if you're, or even 10%. 10% is still dangerous, right? But usually in classification, what you do is, if you want to know whether this item belongs to class A or class B, it's just, if there is no moral judgment or some other concerns, it's usually 0.5 that you would use, okay? So if you look at if you think about this two-dimensional curve and think about the 0.5 case, that 0.5 will be giving you a decision boundary. So there's this thing called here, decision boundary, which is usually at 0.5 threshold. There's, if you go over here, there's more probability that your data point belongs to class B than class A. If you're here, there's no more probability that your data set belongs to class A than class B. Okay? So there will be this decision boundary. And then once you get to two-dimensional, you now realize that figuring out this decision boundary is harder than one-dimensional. It's easier to mess up the decision boundary if it's two-dimensional, because the line could be drawn like this or that. Some of these decision boundaries won't be that good, right? Do you agree? You really want to have the right one. And there are basically two different approaches for the decision boundary when you're trying to make a straight line decision boundary. One is linear regression, the other one is support vector machines, which we will go over later in this class. Okay? Those are cases when you have straight ones. Okay, so the linear regression formula that would determine this using the two predictors will look like the following. The predicted probability is given by 1 over 1 plus e to the negative. And what goes in here is similar to that multiple linear regression. Okay, multiple linear regression formula was like a plus beta 1x1 plus beta 2x2. And I talked about last time how to get these values. Beta 1 and beta 2 was, for the multiple regression, there were some formulas, right? So basically your goal is to come up with the values A, beta 1, and beta 2 that would do the best job in classifying the two groups, group A and group B. Okay. And that's called logistic regression. I mean, if you understood what I said so far, then you know what logistic regression is. Sounds simple.